Alright, so in this video we go over section 3.2, the chain rule and the general power rule. So when are we going to use this rule for differentiation? Well, so suppose, okay, let me write something right on the side. So suppose that we want to take the derivative of a function like this, f of x, and I believe we did something like this in the previous in the previous chapter, x plus 1 squared. Well, one of the strategies for this is to square the binomial to simplify the function, and then take the derivative of each term, which is not, it doesn't seem like, like too much work if you ask, so that's final answer. Take the derivative of each term after foiling the binomial. However, what if your function f of x is, well, very similar, x plus 1 to the third power? Or what about, third power might be a little bit painful to expand. However, the higher the power, like to the power 4, to the power 7, x plus 1 to the power 100, imagine having to FOIL that 100 times. It's simply not practical. So in this case, we need to consider these functions more like a composition function and separate the parts into two, and well, you'll see how. So uh, in this case, well, the chain rule here, well, this is supposed to be the chain rule, not the product rule. So the chain rule is used when we have a function that can be viewed as a composition function. So what we're going to do is consider the function, like the function, again, the same one. Let me give you the example. F of x equals x plus 1. Let me do this to the third power instead. Or let me actually call this, instead of f of x, let me call this y, because I'm going to use I don't want to use the letter f two times. So this can be viewed as the composition of the function uh, f of x equals to x cubed, and the function g of x equals x plus 1. If you do the composition f composed with g, what we're doing is plugging in x plus 1 wherever we see the x in the function f, and that's why we would get this function right here. And well, so the way to find the derivative of a function using the chain rule is by differentiating you can think of these functions as multi-layered functions, so let me erase all this right here. Like, you can see this function as a two-layered function, an outermost function, the outer layer, and the inner layer. So the outer layer function is like differentiating x cubed. So what we're going to do is differentiate the outermost function, which in this case is f, leave g inside the same, and multiply by the derivative of g. Well, of course, in this case, I think looking at examples will make more sense about what we're talking about. So this is what we're going to do. Find the derivative of each function, that is, find y prime. Well, in this case, we're going to do the following. So think of this function as a composition of the function, the inner function and the outer function. The outer function, you can think of a function like x to the fourth power. So what we're going to do is this 4 will jump out in the front, subtract 1 to get the following. So that'll be 4 times x squared plus 3x minus 7 to the 4 minus 1, which is 3, times the derivative with respect x of the function inside, which is x squared plus 3x minus 7. So imagine having to FOIL that trinomial x squared plus 3x minus 7 4 times. It's simply not so practical. So let's do the chain rule instead. Well, so that'll be 4 times x squared plus 3x minus 7 to the third power times the derivative of x squared minus 3x minus 7, which is 2x plus 3. And in this case, you don't have to simplify any further. I mean, think of having to write this expression and FOIL it 3 times, and then on top of that, multiply by 2x plus 3 each of the terms. So no need to do that. And that's simply what we do. All right. Let's look at letter B, and well, for letter B, well, we have this a radical function that we need to rewrite in terms of rational exponents. Well, so to get y prime, again, have this to jump in the front, subtract 1, and then multiply by the derivative of the inside, just the same way we did it in the previous example. So 1/2 times x cubed plus 1 times 1/2 minus 1, which is negative 1/2, times the derivative with respect x of the function x cubed plus 1. That's going to be, well, number 1, this negative 1/2 power, I need to rewrite it in the denominator as the 1/2. And then the derivative of x cubed plus 1, that's a 3x squared. And then we're going to do two things at the same time. I'm going to write this in terms of one single quotient, and I'm going to change this rational exponent into radical form. That is 3x squared divided by 2 square root of x cubed plus 1. Final answer. All right, so now let's look at letter C. And for letter C, it's something I mentioned almost at the end of the previous video, in the second to the last example, in which technically here we have the quotient of two functions f and g. Recall from the previous topic, and well, let me actually go back to 3.1 again and showed you that example. Over here, we had something similar, in which we needed to differentiate the number 1. Every time you would do that, this has to go to 0 always. And well, that's in a way, that's to me a little bit, redundant or like unnecessary. So instead of using the 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 quotient rule, we are going to use the chain rule. And I mentioned back when I covered that example that we would make this problem in a lot shorter way. So for example, number 1, I'm going to rewrite this polynomial under the radical. That's going to be 4x cubed plus 7x plus 21 to the 1/3 power. That's because the index is 3. The index tells us the denominator of the rational exponent. And also, keep in mind that this whole thing is raised to an invisible 1 power. The whole thing under 1. And then I'm going to move this expression to the numerator as 4x cubed plus 7x plus 21 to the negative 1/3 power. And now we are ready to use the chain rule on this expression, on this function. Y prime will be, well, negative 1/3 times 4x cubed plus 7x plus 21. And well, so again, we're doing the same chain rule. Multiply the exponent in the front and then subtract 1 to this exponent. That's negative 1/3 minus 1, which is 3/3. Negative 1/3 minus 3/3, that's going to be minus 4/3. and then that's times the derivative with respect x of this quantity over here, so that's 4x cubed plus 7x plus 21. And well, on the one hand, let me write this with positive exponents. That is 3 times 4x cubed plus 7x plus 21 to the 4/3 power. The whole thing under 1, but don't forget this negative in the front. And I'm going to take the derivative of 4x plus 7x plus 21. So that's going to be 4 times 3, which is 12x squared, and the derivative of 7x, which is 7. The derivative of 21, which is a constant, is just 0. So let's just rewrite this into one single quotient and change this rational exponent in the denominator into radical form. So 3 times the cube root of 4x cubed plus 7x plus 21 to the 4th power. The whole thing under 12x squared plus 7. And this is final answer. And these were 3 examples in which we apply the quotient rule. Of course, there's more that we can do beyond these techniques. For example, we can combine what we learned in this section, which is the quotient rule, along with what we learned in the previous sections, which is the product rule and the quotient rule. And later, we are going to apply this to all these together into functions that contain logarithmic functions, exponential functions, etc. So let's have a look at the next topic. Well, again, I mean, really the chain rule, another way to visualize this is, like considering the general power rule. You have a function, some function to whatever power, g of n, g of x to the nth power. Essentially, we are doing the general power rule that we did for, or rather, for differentiating x to the n. However, what we do is multiply this a bit further by the derivative of the quantity inside of the radical or inside of the parentheses, and later on it will be the derivative of the exponent of an exponential function, or the derivative of the expression inside of the argument of a logarithmic function. Now let's combine using multiple rules. So let's find the derivative of each function here. So notice in this case, we have the product of two functions, f and g. But at the same time, if you observe these two functions, each function looks like the composition of two functions each, like this one function looks like the combination, like the composition of f of x equals x cubed, and let me just call it simply f equals x cubed, and g equals x squared plus 1. This composed over here would give us this big function. On the other hand, the second function looks like the composition of f square root of x, and with g equals to x plus minus 3. If we compose this function, we should get as a result that big function, right? So in this case, we are going to combine the product rule along with the chain rule at the same time. But before doing that, we need to change this radical form into rational exponent form. X squared plus 1 cubed times 2x minus 3 to the 1/2. So we're ready to do this. So let's find y prime equals to x squared plus 1 quantity cubed times the derivative with respect x of the second function, which is 2x minus 3 to the 1/2, plus 2x minus 3 to the 1/2 times x squared, oh, not x squared, actually, the derivative of, with respect x, of x squared plus 1 cubed. Alright, let's do one thing at a time. So number one, we're going to use the chain rule over here. We're going to use the chain rule over there. Alright, so let's see what we get. So y prime equals to, that's x squared plus 1 cubed times the derivative of the quantity I have highlighted in yellow, that's 1/2, 2x minus 3 to the negative 1/2, times the derivative, be careful here, because we still need to further differentiate the 2x minus 3, and differentiating that to x minus 3, its derivative is 2, and then plus 2x minus 3 to the 1/2 times the derivative of x squared plus 1, the whole thing to the third power. So we're going to do 3 times 3 minus 1, which is 2, x squared plus 1, and then times the derivative of x squared plus 1. So that's why we call it the chain rule, because it's like taking the derivatives in chain, you know. So the derivative of this x squared plus 1 is 2x. Alright, let's see what can we do to simplify this a bit further. Well, notice number one, how these 2's cancel. Also 3 times 2 equals to 6. And this x to the negative 1/2 will go to the denominator as positive 1/2 and later as a radical. So let's do one thing at a time. X squared plus 1 cubed over quantity 2x minus 3 to the 1/2, and 2x minus 3, we can actually start writing that as a radical form, 2x minus 3, and times, I'm going to write this 6x in the front. Let me actually rewrite this whole thing. Six x square root 2x minus 3 over, oh, not over, actually that times, let's see, x squared plus 1 squared. And last but not least, we can change this radical expression, a rational exponent expression into radical. Okay, so let's see, so that's going to be x squared plus 1 quantity cubed over the square root of 2x minus 3 plus 6x times the square root of 2x minus 3 times x squared plus 1 quantity squared. And this would be final answer. This is fine as a final answer. Well, again, it's going to depend on how Hawks is gonna, our homework system is going to accept it. Most likely it will take this as a final answer. However, at the end of this video, I'm gonna go over how to simplify this a bit further. In the meantime, let's go over letter B, and then I'll go back to letter A about how to simplify that. All right. Well, on the one hand, for letter B, notice here we have a combination of two different rules. Number one, we will be using the chain rule along with the quotient rule. How do we know that it's a quotient rule? Because we have a quotient of two functions here. So that's how we know that. Now, let's rewrite this as 2x minus 7 over 3x plus 4, the whole thing to the 1/3 power. So let's use the chain rule. Y prime equals to 1/3 times the whole thing to x minus 7 over 3x plus 4 to the 1/3 minus 1, which is negative 2/3. And then that times the derivative of this quantity inside of the parentheses. That is the derivative with respect x of 2x minus 7 over 3x plus 4. All right. So let's find the derivative of this quotient, by the way. Let me go over here. I might need space for this later. So this will be 1/3. By the way, you might want to change this negative rational exponent into positive rational exponent by doing the following. Whenever you have, let me do this real quick. Whenever you have like a over b raised to negative m over n, you can change the sign of this rational exponent into a positive m over n, provided you flip the fraction inside of the parentheses, and that's what I'm going to do here. So I'm going to multiply by 3x plus 4 over 2x minus 7. The whole thing, instead of negative 2/3, that's positive 2/3. All right, and let's take the derivative of this using the quotient rule. So the quotient rule for that, well, that'll be the quantity in the denominator, that is 3x plus 4 times the derivative of, with respect x of 2x minus 7 minus 2x minus 7 times the derivative with respect x of 3x plus 4. The whole thing divided by 3x plus 4 squared. All right, so let's just simplify this derivative over here. Let me do this real quick. So I'm going to need more space for what I'm going to do for the previous example. And well, let me actually shrink it a little bit. Whoops. Okay, no. Yeah. Okay, so we are going to have 1/3 3x plus 4 over 2x minus 7 to the 2/3, and well, that's going to be 3x plus 4 times the derivative of 2x minus 7, which is 2, minus 2x minus 7 times the derivative of 3x plus 4, which is 3. The whole thing divided by 3x plus 4, quantity squared. So now let's see what else can we do. So number one, 1/3 times 3x, and you know what, let me expand this exponent to both numerator and denominator. 1/3 times 3x plus 4 to the 2/3 over 2x minus 7 to the 2/3 also, for a reason that you will see. So this will be in the numerator. We are going to end up with times 3x times 2 and 4 times 2. That's 6x plus 8 minus 2x times 3, negative 7 times 3. In this case, that's going to be minus 6x plus 21, because negative times 7 times positive 3 is negative 21, times the negative in the front becomes a 21. And see what is going to happen here. Notice how this 6x's go away, and 3x plus 4 quantity squared right here. In the end, we are going to get the following. We're going to end up with the sum of 8 plus 21, which will be 29. Now, the reason why I splitted this 2/3 power is because notice we have this 3x plus 4 to the 2/3, 3x plus 4 to the second power. All we need to do is subtract 2 from 2/3. Now, in order to get that, well, times 1, 3, and 3, 2 minus 6, that's going to give us negative 4/3. So we are going to end up with the following, which is 1/3 times 3x plus 4, and the result of combining these two is, what was that? 2 minus 6, negative 4/3, and that times 8 plus 21, that's a 29. And in this case, that reduces to the following. That's 29 in the numerator, and in the denominator, 3 times 3x plus 4 to the 4 over 3. And well, changing this back to radicals, that's a 3 cube root of 3x plus 4 to the 4th power, all under 29. Final answer. All right? This is final answer. Now, let's go back to example to letter A and see how can we further actually simplify. And yes, there's a way to write this in a more compact way. On the one hand, number 1, notice this x squared plus 1 is raised to the 3rd power, and notice this x squared plus 1 is raised to the 2nd power. So we notice x squared plus 1 is then, for that reason, our greatest common factor, and I'm going to factor the lowest power possible, which in this case is x squared plus 1, and I'm going to be left with 1 power of x squared plus 1 over the square root of 2x minus 3. Well, again, and then actually plus 6x times the square root of 2x minus 3. Alright, again, if you would distribute this back again, you would get x squared plus 1 cubed that we originally have, then this x squared plus 1, this whole madness right there. Alright, but it looks like I forgot to write these two over here. Okay, now, and let me also erase this brackets. So this is the same as having, let me erase this, make it smaller. Notice this can be rewritten as over 1. And we're going to multiply by a least common denominator, that is 2x minus 3, 2x minus 3. Alright, so what is going to happen when we multiply this to, well, when we multiply 2x minus 3 times itself, the radical will disappear and we are going to be left with just 2x minus 3. So that'll be x squared plus 1 squared times one big fraction, x squared plus 1 plus 6x that multiplies 2x minus 3, the whole thing divided by the square root of 2x minus 3. And let's keep simplifying this one right here by distributing the 6x to get, that's an x squared plus 1 outside, quantity squared, times x squared plus 1 plus 6 times 2, which is 12x squared, plus or rather minus 18x. The whole thing over the square root of 2x minus 3. And well, in the end, well, let me make this read better. In the end, well, combining this together, we should get the following. That'll be x squared plus 1 squared, that's times 13x squared minus 18x plus 1 divided by the square root of 2x minus 3. And that's what I would call a final answer here. That's a more compact way to write this as a final answer. The reason I'm going this extra mile is just to show you what to do in a situation in which, well, like I said, if we were, if I gave something like this on an exam, I would have let you give me just this as a final answer. But sometimes homework systems, like the online homework system, like the one that we're using, might be a little bit picky and might want a more simplified, a more reduced final answer. So I would go this extra mile. So again, uh, this is what to do in each situation. And the same was done over here to keep simplifying this to a more simpler solution here. And well, so this is the end of this video. This finishes the chain rule. I'll see you in the next section.